Well, can you give us an idea of a typical application, and in particular, how big it is, how long it takes to develop?
Sure. So there are two or three, as I said, different kinds of applications that we tend to develop. I think one that's a good representative is the forecast manager. So a forecast manager is an application that will forecast demand, customer demand for products at various locations, various stores of a retailer based on an historical analysis of how those products have sold at those stores over the last 2 to 3 years. It takes into account special events like promotions that are in force, and it's actually a pretty complicated set of calculations. It involves some regression analysis, and it's pretty involved. So we generally, when we have a customer, what we'll do is every week or maybe even every day, we will generate new forecasts for them in a big nightly or weekly batch. And we'll calculate the next 52 weeks of forecasts for all their products at all their stores. After which most retailers have a group of employees who go through and review those forecasts, and if they find things don't look like they have imagined, because it's forecasting, it's not, it's not an exact science, they'll want to get in and do some tweaking, make some adjustments to them. Maybe they think that some estimates of increased demand are too high or too low, and they'll want to actually make some changes. So Forecast Manager application is responsible for generating all these forecasts, allowing forecasters, the employees at a retail organization, to go through and drill up and drill down and try to understand these forecasts, and also allow them to make changes to the forecast, tweak them, what if them, et cetera.
And they can use these forecasts to predict sales and do
Correct.
Inventory
Yep.
sorts of things and so on. I mean, it's
correct.
kind of central to their planning.
It's very central to their planning, yeah. It's typically hooked up with replenishment systems as well. So once they approve their forecasts that we've suggested for them, they'll then send those forecasts down to a replenishment system, which will actually make orders and cause goods to be put on trucks or on ships or whatever.
And I imagine with all this data that there are kind of heavyweight calculations, functional requirements that the forecast manager has to satisfy.
That's correct. That's correct. And what's interesting about it, and what I found, particularly in working in the retail domain, was surprising. Let's put it that way. Every different client has slightly different business requirements that make it very difficult to design a completely generic product. So there's always a bit of client-specific business rules that you need to take into account, and configuration. It's not like a shrink-wrap product at all. So it really is, when you want to sell this to a new client, even if it's a product that's very similar to one you've released before, you have to do a fair amount of, you have to staff it up with a development team and do or extend an existing requirements analysis and do some custom implementation.
So when you say product, before you were talking about software as a service, your products are really services.
That's correct, yes.
Okay. And what I'm hearing is that you don't want to have to do a separate forecaster for every one of your customers, but there are individual pieces. Each customer has their individual needs, and so you need some solution for them specifically, but you can't have a general one for everybody.
That's correct. That's correct. That's one of the core parts of the problem. It makes it hard.
Okay. Now, how about on the non-functional side? What sort of interesting non-functional characteristics do these applications have?
Yeah, you can break them into a couple of categories. One is, you asked earlier about how we get data and how we load it. So that implies that there's a batch operation that has to load all these data that come into our database. The batches tend to have pretty tight timing requirements. So for example, when we do forecasting at the end of a week for the next week's orders, we typically get the sales data, the revised sales data that we use in predicting. We'll get that sometime late on a Friday evening, and we may get any number of other kind of data from the customer as well that we need to use in prediction. And we'll have to have the forecasts all regenerated and ready for inspection and modification by the forecasters when they arrive by 8 a.m. Monday morning, right? So there's a batch window. And that batch window is one that is a very hard deadline. We have, if we can't do all the work within that deadline, we have a service level agreement with our customers because we're selling this as a service. And if we don't meet our batch window, then we're in violation of that agreement. That has financial implications, et cetera. So batch requirements are big. We also have a nightly batch, which has a much tighter window and doesn't consume as much data.
So in the weekend situation, is that enough time for you to deal with things? Or, I mean, how much of that weekend is consumed with actually computing?
Yeah, so that's a good question. It depends largely by client. For our bigger clients, we have one that I think their app is now, it's over 11 terabytes of data that we have to maintain and let them use. And what we do is we actually partition the database over many different nodes on the cloud, so that we can meet this batch window. And what we find when we're scaling these up is we have to do some experiments to decide, how big, how fat can we make one database in order to meet our batch window, to load not just to do the calculations, but just to load the data to begin with, because it takes a while to load 6 terabytes of data. So we have to scale ourselves and partition it so that we can load all the data, perform all the calculations within the batch window. And there's always a trade-off between, the more you can decrease your batch time if you throw more machines at it, but then that increases your costs, our company's costs, which we have to eat. All right, so we're always trying to optimize that and hit the sweet spot.
So what I'm hearing is that you're making use of many or a large number of fairly heavyweight server nodes on the cloud that are cranking pretty much full-time over the weekend.
That's correct.
To make sure you hit your deadline for Monday morning.
That's correct. That's correct. And one of the things that's interesting about deploying this as a service has everything to do with that problem. So traditionally, when a retailer would want a forecasting application, that retailer would have to buy and maintain all of the machinery he or she might need in order to generate those forecasts, even though you're only going to do it every weekend. Sorry. So what typically happens with the forecasting application is it's a lot of heavyweight work on the weekend, but then during the week it's not so much. And so our solution scales so that we actually scale up over the weekend in order to do all this data loading and calculation, but then we scale back down to a much smaller footprint after all those calculations.
So you're taking advantage of the fact that you can get elastic computing resources off the cloud and only pay for what you need.
Precisely.
Okay. So I interrupted you before when you were talking about the non-functional requirements. What else is there?
So batch requirements was the one category. The other category are interactive requirements. So users are going to, as I mentioned, after we generate all these forecasts, they're going to want to go through and inspect them and analyze them and drill up and drill down and make analyses and maybe even make modifications. So that's a large set of data that they need to operate over. And anytime you have users doing interactive queries over large data sets, you have the potential that queries and operations can take a very long time. So in addition to our batch window, we also have to design and partition accordingly so that queries will be, user operations will perform in acceptable times.
And I'm assuming you've kind of mentioned that reliability is very important.
Mm-hmm.
Okay, you have to get the thing done.
Yeah.
How about accuracy of these computations? How do you deal with that?
Yeah, so usually through a separate process. So LogicBlox has a dedicated data science team that works with big retailers who are very familiar with their own data to do accuracy analyses. And we tend to do this by running our forecasting offline and comparing it on old data and then comparing it with actual sales data. And so there are some metrics we use called mean percent error that you'll use to decide whether your forecasts are sufficiently accurate, if they're within a certain mean percent error of the actual sales. And so we tend to do that offline. And then if there are any changes to the algorithms, the science algorithms, we roll those into the service so that it'll be available the next week when we do the next analysis. So
some real significant non-functional requirements in order to make all this work in a fashion that can satisfy your customers.
Correct.
Okay, how about the architecture itself, let's say, of the forecast manager? What makes this, this particular application architecturally interesting?
Okay, so I think from an architecture standpoint, what makes this architecture most interesting is the distribution aspects, the services-oriented design of the whole thing, and how each of the distributed nodes talk to one another. So I have a diagram we can take a quick look at. This is a multi-tier diagram. I'm not showing the top tier because the top tier is basically a web browser, right? So all of our clients, their top tier or presentation tier would be their web browser. They're going to be running HTML5, JavaScript applications running in their browser that are periodically going to make service calls to a uniform location on the cloud. Those requests, those HTTP service requests, will all go through this front end node that I'm showing here in this diagram. We consider that the middle tier, right? So the front end of our application is a middle tier that has a couple of databases running on it, which I'm showing there. One of them is largely the one called UI0, is hosting services which do things like either directly answer queries or proxy them down to other nodes that actually contain a slice of the real data. And so that data tier level that I'm showing in the diagram actually has multiple. I'm abstracting it by just showing two, but there could be up to 50 or 60 or 100 of these things, depending on the size of the data. Each one of them is the same in terms of what code they're running, but they have a different partition of the data that they're responsible for. And each one of them is running a web server that's hosting services that answer queries, right, or do updates. So typically in this architecture, you don't see this much when you're running the app from your browser, but you'll click on a link to go drill down into the results of some query. That will issue a request that goes to this front end node, which may then delegate to one or more of those data tier nodes to gather some data or perform some updates, put it back together, and then it gives you a response. And all this has to work very quickly.
So as far as architectural style, would you say this is a three-tier architecture?
Yes, yes.
And complicated by the fact that you partitioned your data across many, many nodes.
Correct, correct.